Hello and welcome to my talk. My name is Bohdan and today I will present you BWoS, formally verified block-based work stealing for parallel processing. It is a joint work of my colleagues from Huawei Dresden Research Center, Technische Universität Dresden, MPI-Institute for Software Systems, and Shanghai Jiao University. The motivation for our work has been the proliferation of parallel processing in the runtimes of programming languages, for example, Java and Golang, in the servers and user space libraries like Rust's Tokyo, and in primitives for parallel programming languages like Silk or frameworks like Intel thread building blocks. In each of these use cases, there is a necessity to distribute workload over a number of cores. So what kind of strategies do we have to implement this workload distribution? Well, there are three main approaches. So one and very simple approach would be to rely on a single multiple producer, multiple consumer queue. And the main benefit here is that as long as there are items in the queue, no core or thread will starve. Unfortunately, the drawback of this approach is as the number of cores or thread accessing the queue becomes large, the contention increases, and the performance can just plummet. The alternative is to give each core a separate dedicated queue. And the good property of this approach is that the single queue performance is very high, and there's very low overhead due to any sort of synchronization. But it also has a drawback that if the workload is bursty or irregular, then the performance of the system will still suffer, because some of the cores will be overloaded while others will be idling. And work stealing is an approach that aims to achieve a reasonable trade-off between these previous two approaches. So let's look into it in the details. So with work stealing approach, each core or thread, which we call worker here, processes tasks from the queue that's associated with it. So it has a dedicated queue. And if the processing yields new elements, it puts them into the very same queue. And in case the queue is empty and there is no element to get to it, the worker acts as a sieve. It chooses a stealing victim, a queue that belongs to a different worker, and gets an element from it. So this approach is a middle ground between the workload balance of MPMC queue with the performance and scalability of the single worker queues. However, how does this approach work in practice? As the workload items become more and more fine-grained, the overheads of the queue operations increase, and the queue can become even a bottleneck. So, for example, a popular Golang JSON processing library called CodeJSON relies on spanning Go routines when processing large JSON objects. And here we can see a flame graph for the benchmark of JSON decoding. And we can see that only 51% of all cycles are spent on processing the workload. On the other hand, we can see that coroutine scheduling and garbage collection take together 27% of cycles, and the implementation of a Go programming language, these are implemented using work stealing. Or we could turn our attention to the experience of Rust Tokyo library author, who has spent lots of time optimizing the work stealing queue implementation in Tokyo, because in Tokyo the workload items are rather small and the work stealing queue overheads also become significant. So the conclusion that we've reached is that work stealing requires new designs and approaches to satisfy the requirements of applications with fine-grained tasks. However, what makes work stealing slow? Our investigation has uncovered three main sources of overhead, and that's the overhead of barriers in queue owners' operations like put and get, overheads due to the victim selection policy when choosing a queue to steal from, which, however, I won't have time to cover in this talk. And finally, there's interference between the owner and the thieves when stealing actually happens. So first, we cover the overhead of barriers in the owner's operation. So the design goal of work stealing queue is to ensure the high throughput in the situation when there are no thieves. And in this case, the performance limit for us is the performance of sequential queue. However, when we compare the performance of existing state-of-the-art queues with sequential queues, we will see that they are 4 to 5 times slower. And the reason for this is that because thief can steal at any moment of time, work stealing systems have to rely on strong atomic fences in every owner's operation. And this causes significant overhead that we observe here. Another source of overhead appears when thief actually steals from the queue, and it's a cache interference with the owner. And as first thief will read the global queue metadata, which owner also accesses to put and get entries from the queue, and then potentially over the queue data itself. And our experiment shows that when the stealing rate is 1% of owner's operation rate, the overheads can reach 18% when the thief is in the same NUMA node and up to 25% when it's in a different NUMA domain. To solve the outlined problems with classical work stealing, we present our block-based work stealing approach. And it's based on 3 main design decisions. To speed up the owner's operations, BWoS introduces block-based synchronization, which removes barriers from the majority of put and get operations. To alleviate issues with size-based stealing policies, we design a randomized stealing policy, which does not require accessing the global queue metadata of stealing victims. Finally, to remove cache interference over the data and metadata, this policy reduces the probability that thieves would steal the block on which owner is currently operating. The key design decision of BWoS is separation of the queue into multiple equally sized blocks, which contain individual workload items. So for the purpose of presentation, I will depict the individual queue as a ring buffer of blocks. So not workload items, but blocks. And to remove the cost of most synchronization overheads that affect the performance of the queue owner, we divide the blocks into those owned by the thieves, which contain elements eligible for stealing, and those owned by the owner, which are either empty or not eligible for stealing. And this allows us to perform what we call block-level synchronization. The synchronization between the owner and thieves with the use of strong atomic barriers happens only on the level of blocks when crossing the block boundary. For example, when the get operation needs to consume the entries from the next block, it takes over the block from the thieves. And when it has finished producing the block to its limit, then the owner will grant the block to the thieves. On the other hand, inside of the block, the owner can put and get entries using relaxed atomic without any synchronization with the thieves. And this forms the fast path of our algorithm, which we can see here for put and get operation. And this allows us to achieve performance close to the theoretical maximum. To gain the benefits of size-based policies while avoiding the overheads due to cache interference between the owner and thieves, we introduce a probabilistic stealing policy. And this is enabled by the fact that with BWoS, each block has its own metadata, its own dedicated metadata instance. And the main idea of the policy is that instead of reading the queue size directly, we estimate it via sampling, where we merge the queue size estimation and stealing into one step. Let's see how this works in practice. Let's say we have a queue which is empty, and owner acts as a thief. And to steal an element, it will randomly select a queue to attempt stealing from, and it will randomly select a block in the queue. So in this case, the block is empty, and the thief will retry several times until it finds a block that is eligible for stealing, or it will give up under the number of tries. When combined together, block-based synchronization and randomized stealing greatly reduce the performance overheads due to interference between thieves and the owner. And the main reason is that thieves don't have to access the global queue metadata neither for victim selection nor for stealing, and with high probability will operate on a different block than the queue owner. Due to block-level synchronization, fast pass, and the novel stealing policy, BWoS is a complicated algorithm with a high number of atomic instructions. And to ensure the correctness of BWoS, we were designing it with the direct support of lightweight formal methods. For this purpose, we have relied on VSync toolkit, which provides us model checking together with weak memory barrier optimization. To use, we think we have implemented BWoS in C using the strongest sequentially consistent atomics, as well as a test client which comprehensively exercises code paths of our queue and states the necessary properties of the concurrent algorithm via asserts. We think we have verified the following properties, like memory safety, data race freedom, loop termination, and queue consistency. Furthermore, we think has optimized weak memory barriers for us, completely removing all most costly sequentially consistent fences and converted majority of atomic accesses to relaxed atomics. Now, does weak memory barrier optimization matter at all? Here we have compared the performance of optimized and unoptimized BWoS, and the same for the popular ABP work stealing queue. And here we can see that BWoS has up to 5.4 times higher throughput when it's optimized compared to an unoptimized version, while ABP queue struggles to get significant performance benefit out of the weak memory barrier optimization. And this stresses the benefits of designing algorithms in such a way that the benefits of hardware weak memory models can be productively utilized. We have also performed micro benchmarks comparing BWoS with other state-of-the-art algorithms. And when comparing throughput, the higher the better. First thing we can see is that BWoS compares very close to the ideal performance given by the sequential queue. And furthermore, when 10% of all items are stolen, it has up to 30 times higher throughput than state-of-the-art algorithms. Returning to the flame graph of GoJSON benchmark, which measures the execution time of parallel JSON decoding, we can see that the percentage of cycles dedicated to the workload processing has increased from 51 to 71%. While the garbage collection time has decreased to only 9% of all cycles. In total, GoJSON benchmarks experienced 28% speed up on average on ARM architecture, but I'll have to refer you to the paper for more detailed graph. However, we can conclude that BWoS can improve performance of real-world computational workloads. We have also applied BWoS to Rust Tokyo framework. We have replaced the work stealing queue that's available in Tokyo by default with BWoS, and we have built throughput latency and throughput CPU utilization graphs for using WRK benchmark for Tokyo's HTTP server called Hyper. And we can see that BWoS can achieve up to 12% higher throughput while reducing CPU utilization by 71% and latency by 7%. Thus, we can conclude that BWoS is beneficial for IO-heavy workloads too. Furthermore, we have made these changes available to the open source community. So as a conclusion, I would like to first note that so far we have applied block-based approach to two algorithms. In this talk, I have presented BWoS, and before that, we have applied this approach to producer-consumer queues with barbecue. However, we believe that this approach can be used for many other concurrent algorithms, and we would like to encourage both industry and academia to explore this approach to other algorithms. And finally, we believe that to utilize modern hardware, which has deep and complicated cache hierarchies, which has weak memory models, the formal methods will become the main tool which will ensure their correctness, and thus will enable us to design more and more complex algorithms which actually utilize the features of the hardware. Thus, verified software will and can be faster than unverified. And with this, I thank you for attention, and I'm looking forward to your questions.